Hi, my name is Richard Lam, and I'm going to present to you forecasting ozone for the San Francisco Bay Area during the 2020 season. The Bay Area Air District consists of 9 counties in the Bay Area with 8 million people living in it. Our summer season goes from May 1st to October 31st, and we forecast ozone. We consider exceedance in ozone when the 8-hour ozone is over 70 ppb, and high ozone does play a role in impacting human health. There's microclimates during the summertime in the Bay Area. Inland area is much warmer than the coastal area. It's the differential heating in a short distance that drive the daily occurrences of the sea breeze through the Golden Gate into inland area. For ozone formation, there are weather factors and chemistry. For weather, we look at sea breeze, marine stratus, inversion profile. And then for chemistry, we need to know the NOx and the VOCs in the Bay Area. And we look at the traffic level and also wildfire emission. We tend to get most of our ozone exceedances in the eastern and southern part of the Bay Area. These areas are the hottest and less likely to be impacted by the daily sea breezes. We obtain traffic data for the Bay Bridge from the MTC. So in January and February, the traffic level is around 100% of normal, which is what we expected. But then the pandemic hit in the middle of March, and that's when the traffic level sharply dropped to less than 50% of normal by late March, going until mid of April. Then the traffic level slowly rebound, and by the time we get to October, the traffic level is back to 80 to 85% of normal. I want to learn about the impact of COVID-related shutdown on ozone. So I submit this abstract on August 12. About a week later, the largest wildfires in California history impacts the Bay Area, starting from August 18 through October 8. With that, I changed my study goal to look at both the pandemic and also the wildfire impact on the ozone for the Bay Area. You may have seen the orange skyline image for San Francisco on national news on September 9th. The skyline imagery corresponds to that day. You can see the smoke covered area from Southern California all the way up to Oregon and west into the Pacific Ocean. And then if you look at the image a week earlier, the smoke was not as widespread, but it was mixing with the marine stratus along the coast. Compared to a year earlier, it was just a typical summer day with no smoke influence. 2020 was a historical year for California wildfires. The top 6 of the top 20 largest California wildfires happened in 2020. 40% of the top 20 largest fires happened in 2024 acreage. The map to the right shows you the area where the fires happened in the last 5 years, and the red shaded area shows you 2020 wildfires. And one thing to note is that they are all very close to the Bay Area. Literature review also shows that the wildfires produce daily enhancement to ozone of about 10 to 20 ppb at individual sites. 31% of summer days with ozone exceedance would not have occurred if there's no wildfires. So now I'm going to show you the air quality in the Bay Area overall for 2020. The graph on top shows you ozone, while the graph below shows you PM 2.5. The ozone season starts on May 1st, marked by the red line. The blue line shows you data for 2020. The gray line shows you the 5-year average data. And then the light blue shading shows you the 20-year high and low. And one thing to note is between May and August, the ozone is generally less than what we saw in the last 5 years. But then the fire season hits, and that's when you see the ozone is higher than the 5-year average. You can also see the similar trend for PM 2.5. In order to understand the impact of the pandemic-induced traffic reduction and the wildfires, we need to find a way to filter out weather variables. And in order to do that, we'll use our in-house forecast regression. The forecast regression is based on temperature and the strength of the sea breeze. So the hotter the temperature and the weaker the onshore flow, the higher the ozone. Using our regression, then we can forecast ozone based purely on weather factors. And then we have the observed ozone, which is the actual ozone measured by our sensors. If the regression ozone is larger than the observed ozone, what that means is that our regression kind of overestimated how much ozone is in the air. So the air is actually cleaner than what the weather factor is saying. On the other hand, if the regression ozone is less than the observed ozone, that means the air is dirtier than what the regression or the weather factor is expecting. And with that, we can look into the data now. I plug in all the data, and now we can look at the regression ozone versus the observed ozone in 2020. The regression is in blue line, and the observed is in red line. And when you subtract the observed from the regression, you get the graph to the right, and that's the residual graph. So for May, June, July, and August, we were under the impact of pandemic, so less traffic. So the residual is mostly positive. That means the regression overestimates how much ozone is in the air, and the air is actually cleaner than what we expect. And then in the middle of August, we start to have wildfire influence. The residual goes from positive to negative. And the regression underestimates the amount of ozone in the air. So the air is actually dirtier than what we expected. You may wonder why in May and June there are a lot of negative values here. I think this is a bias in our regression model, and I will try to explain to you how we're going to resolve that in the next slide. I use the same methodology that I did with 2020, but now apply it to the data from 2009 to 2019 to create a baseline. And the result is shown in the red line. That's the 10-year average data from 2009 to 2019. And one thing you have noticed is in May and June, there is a negative bias in the red line. And then by the time we get to July, August, September, and October, the red line is pretty neutral, just hovering around zero line. As I mentioned in the last slide, there is a bias in our regression, especially in the early season. The reason why is underestimate the ozone is that the regression is based heavily on how hot the temperature gets, and in May and June, inland areas still hasn't heated up significantly, so that we tend to underestimate the ozone concentration during the early season. And that's why you see this negative bias. But by the time we get to July, August, September, temperature is harsh enough inland that that bias go away. And with that, now we can compare 2020 with the baseline of 2009 to 2019 and see if we can come up with a better analysis. And I'll show you in the next slide. And this is the result. From May 1st to the mid of August, now you see most of the residual is positive. That means the regression overestimated the ozone by about 6 ppb during this period. And then the wildfire hits in the mid of August and the value flipped from positive to negative. And during the wildfires, the regression underestimated ozone by about 5 ppb. Note that in late September, the value went from negative to positive. That's when there's a break in the smoke coverage in the Bay Area. And as soon as the smoke returned in late September into early October, the value went back to negative. The fire ended in the beginning of October and the value flipped back to positive. In late October, note that the value went back to negative, and that is due to a transport event bringing dirty air from the Central Valley into the Bay Area, and the regression doesn't do well in this situation. So this graph shows you the PM 2.5 concentration. That shows you how much smoke is in the air. So from August all the way into the mid of August, the Bay Area is impacted by smoke. But then between September 15 to 28th, there's a break in the smoke coverage as seen in the graph. And then the smoke returned after that for a brief period before ending on October 9th. In late October, we have a strong transport event in the Bay Area. So the wind is generally from the easterly direction. And also that was a warming direction due to downsloping. So that's bringing extra pollutants from the Central Valley and at the same time, much warmer temperatures to the Bay Area. And the regression didn't perform well during that time period. It's because of this transport event. So in summary, the pandemic-induced traffic reduction caused the regression to overestimate ozone by about 6 ppb. And then during the wildfires, the regression underestimated ozone by about 5 ppb.